The fourth presentation is titled Negative Sequence Quantities-Based Protection under Inverter-Based Resources, Challenges and Impact of the German Grid Code. The presentation is given by Aboutaleb Haddadi. Dr. Haddadi received his PhD degree in electrical and computer engineering from McGill University in Montreal, Canada. So I think there's some time shift in Canada. Good morning to Canada. He was postdoctoral fellow with the Polytechnic of Montreal from 2015 to 2018. And his consulting experience in the areas of power system, transient analysis, and simulation. And his main research interests include simulation, modeling, and control of power electronic converters with applications in power systems and power system protection. So Aboutaleb, please start with your presentation. Looking forward to it.
Okay, so can you hear me?
Yes, we can hear you loud and clear.
All right, good. Good day to everyone. The title of my paper is Negative Sequence Quantities-Based Protection under Inverter-Based Resources, Challenges and Impact of the German Grid Code. This work has been done in collaboration with the Electric Power Research Institute. So first, some background on what we have done in this paper. Basically, with the increasing levels of renewable energy resources, such as wind and solar generators, the short circuit characteristics of power systems change. And the reason is that mostly these resources are connected to the grid through a power electronic interface. That's why they're called inverter-based resources, IBRs. And this power electronic interface produces fault current signatures, which are different and in some cases more complex compared to conventional synchronous generators. This leads to an anticipated impact on the performance of legacy protection systems, which are set with the assumption of fault current signatures of conventional synchronous generators. Therefore, it is necessary to study the performance of the legacy protection functions under IBRs, identify potential protection misoperation issues due to IBRs, and furthermore, to develop solutions and recommendations to ensure effective protection under high levels of IBRs. The focus of this paper is specifically on the performance of protection elements based on negative sequence quantities. So why are these protection functions prone to malfunction under IBRs? The reason is basically because depending on the type and control, an IBR may exhibit substantially different negative sequence fault current I2 characteristic compared to a conventional synchronous generator. There are two key differences. The amplitude of contributed I2 is smaller and the phase angle is also different. Here you can see a comparison of I2 contribution of a type 4 wind turbine generator to a conventional synchronous generator. So the amplitude under synchronous generator is substantially larger. And basically the reason is because in the absence of grid code requirements, inverter manufacturers have traditionally designed the controls to fully or partially suppress the negative sequence current. So basically because there is no requirement by the grid, the converter suppresses the negative sequence current. Also, the phase angle of the negative sequence current under type 4 wind turbine generator is different than that under conventional synchronous generator. So these two differences may lead to misoperation of protective relay elements which use the amplitude and phase angle of I2. These elements include overcurrent element, which uses the amplitude, directional element, which uses the phase angle, and other protection functions such as fault identification and communication assisted protection, which use these two elements. And to eliminate these misoperation problems, recently some countries have revised their grid codes to require inverters to inject a negative sequence reactive current during unbalanced fault. An example of these grid codes is the recent VDARN 4120 technical connection rule, which we refer to as the German grid code in this paper. And so basically with this background, we have two main objectives in this paper. The first one is to identify potential misoperation of negative sequence quantities-based protection elements due to IBRs. And the second objective is to study the German grid code, basically three aspects. One, to study its effectiveness in addressing the protection misoperation challenges. Two, to study the impact of control parameters on I2 characteristic under the German grid code. And three, to also study the limitations. Of course, like any other solution, the German grid code comes with a set of limitations. So we wish to identify these limitations. So one quick note, in this paper, we only consider full-size converter, FSC, or type 4 wind turbine generator. The findings also apply to transmission level photovoltaic PV resources, but we leave out the doubly fed induction generator, DFIG, or type 3 wind turbine generator, which has been studied in a different paper. So first, let's take a look at the key I2 characteristic under a conventional synchronous generator, type 4 wind turbine generator, and type 4 wind turbine generator under the German grid code. Under a synchronous generator, the contributed I2 is characterized by the negative sequence impedance, because this impedance has a typically low amplitude in the range of 0.1 to 0.4 per unit. And because this impedance is predominantly inductive, the amplitude of short circuit current is large under synchronous generator, and also the phase angle, basically has, the I2 has an inductive nature. By contrast, under type 4 wind turbine generator, the I2 contribution highly depends on control scheme. Under the conventional coupled sequence control, CSC, where the negative sequence current is fully suppressed, I2 has a very small amplitude. So you can see here, because of the I2 suppression control, I2 has a small amplitude. And also the phase angle could be resistive, inductive, or capacitive, depending on the control parameters. So these two differences basically may lead to misoperation problems, and the German grid code is one of the potential solutions to address these misoperations. So under the German grid code, the injected I2, the requirements and the specifications are provided in terms of a characteristic curve here. There are two key requirements in terms of the amplitude and phase angle of I2. The amplitude should be proportional to the negative sequence voltage V2 by a factor K, defined as a characteristic proportional gain. So basically the slope of this characteristic, and the recommended values are between 2 and 6. And also for the phase angle, the requirement is that it should be predominantly reactive. And these two, basically with the increased amplitude and the predominantly inductive phase angle, the I2 characteristic of a type 4 emulates that of a conventional synchronous generator, of course, subject to converter current limits. And this is expected to address the protection misoperation issues. But first, let's take a look at the implementation of the German grid code. Here's an implementation which is realized by modifying the grid side converter control, GSC. There are two key modifications. One is addition of a new or an additional negative sequence current control channel. And the second modification is the current limiter or PQ priority scheme. So the objective here is to generate a negative sequence reactive current whose amplitude is proportional to V2. This is realized by multiplying V2 by a characteristic gain K, and then generating the D and Q axis component of negative sequence current, the desired D and Q axis components, to achieve a desired phase angle. Of course, the positive sequence channel also provides the desired set point of the positive sequence reactive current and also the positive sequence active current. And the current control limiter PQ priority, current limiter PQ priority should distribute the converter current capacity among these four desired set points. The highest priority is given to negative sequence reactive current and positive sequence reactive current. The next highest priority is given to negative sequence active current. And if there is any current capacity remaining, it's given to positive sequence active current. So here's an example. The unbalanced fault created a negative sequence voltage of 0.29 per unit, and the desired set point for negative sequence reactive current amplitude was 0.58. But because of the positive sequence channel requirement, the converter cannot deliver this desired amount of negative sequence current, so the actual negative sequence amplitude will be less than the desired value. But the phase angle, the predominantly reactive phase angle, is nonetheless achieved. So next, what are the important or what are the influential parameters that impact the behavior of I2 under the German grid code? The first one that we identify in this paper is the proportional gain K. Of course, by increasing the proportional gain, it is expected we can basically increase the amplitude of the injected negative sequence current. However, this amplitude is limited due to the converter current limits. So we cannot arbitrarily increase the amplitude of negative sequence current by increasing the gain K. To illustrate this, we consider two examples. One, the lowest value, the lowest gain of K2, and the other, the highest gain of K6. Under K equal 2, the desired amplitude of negative sequence current does not very much exceed the converter current limit, and therefore the actual delivered negative sequence current amplitude is close to the desired value. So the effective gain, which is the ratio of the actual I2 to V2, it is close to the desired gain of K equal 2. But when we increase the gain to K equals 6, the desired amplitude of negative sequence current is basically too high with respect to converter current limit, and therefore the actual delivered negative sequence current has a much lower amplitude. In this case, the effective gain was 2.8 compared to the desired gain of 6. So the conclusion here is that gain K can be designed to increase the level of I2. However, there is a limit to how much you can increase due to the converter current limit. The other influential parameter is the converter current limit setting. So generally there are three limits. One is a limit on the total converter current, ILIM, and there may be an individual limit on the D-axis component of the current and also on the Q-axis component of the current. And in the paper, we show that these limits impact the phase angle of the injected I2. To illustrate this, we consider two scenarios. In one scenario, we basically impose the three limits, a current limit of 1.1 and individual limits of 1. In this case, the converter is able to deliver a predominantly reactive negative sequence current. So basically, the phase angle, the desired phase angle is achieved. But in the other scenario, we only impose the converter total current limit, and there are no individual limits on ID or IQ. In this case, the converter is unable to produce a predominantly reactive negative sequence current. The reason is because in the absence of an individual limit on IQ, the converter control basically gives the entire current capacity to the Q-axis component, and there is no D-axis component to generate the desired phase angle. So the conclusion here is that to achieve a reactive I2, individual limits on ID and IQ are necessary. So together with the previous study, we conclude that with proper design of gain K and inverter current limits, it is possible to increase the level of I2 with desired angular relation of I2 and V2 to reduce the likelihood of protection misoperation. So here is some simulation results to basically illustrate the potentially detrimental impact of inverters on the performance of protection functions, and furthermore to illustrate the effectiveness of the German grid code in resolving the misoperation issues. So we consider this transmission test system, which is a multi-wind park test case. We consider three generation scenarios. In scenario 1, we consider all generators to be synchronous. In scenario 2, we consider them to be type 4 wind turbine generator under the coupled sequence control. So there is no negative sequence current injection under unbalanced faults. In scenario 3, we consider them to be type 4 wind turbine generators. We study the performance of a overcurrent relay and a distance relay, and we apply an unbalanced fault here. So here are the response of the protection element in the three scenarios. In scenario 1, where we have synchronous generator, the overcurrent negative sequence element successfully asserts. It picks up because of the high level of negative sequence current. The directional element also successfully declares forward direction due to the predominantly inductive negative sequence current. And also the fault identification scheme successfully declares phase A as a faulted phase. In scenario 2, where we have the conventional coupled sequence control type 4, we have a number of misoperation issues due to the low level of negative sequence current. The 50Q element does not operate. The directional element mistakenly declares reverse direction, and also the fault identification scheme mistakenly declares phase C as the faulted phase. And under the German grid code, these misoperation issues were fixed due to the increased level of negative sequence current and also the correct phase angle, basically. And here are the limitations of the German grid code, which we have identified in this paper. There are basically two main limitations. One is that inverters are basically current limited devices. Even when they're required to inject I2 during unbalanced faults, the magnitude of this current would be limited. So if this limited magnitude is insufficient to address the protection misoperation issue, then we need to find another solution. And the other limitation is that with the increased amplitude of I2, the amplitude of I1, the positive sequence current, decreases due to the converter current limit. So this reduced positive sequence current may in turn pose a challenge to the performance of positive sequence quantities-based protection. So here's an example. We increase the gain, the proportional gain of the negative sequence, the German grid code characteristic, and we increase the amplitude of the negative sequence current. But if we look at the positive sequence current and its amplitude, the amplitude decreases. So this decreased amplitude could cause other protection misoperation challenges. So the conclusion here is that given these limitations, the full extent of the impact of I2 injection on traditional protection schemes is still unknown, especially when the penetration of IBRs is significantly high throughout the interconnection. So thank you very much. If you have any questions, please let me know.
Thank you very much, Aboutaleb, for your timely presentation. So we have two questions in the Q&A. The first question would be, how can we deal with balanced faults? Is the solution blocked?
Well, when there is a balanced fault, the negative sequence voltage at the terminal of inverter is basically zero. So automatically there is no negative sequence current injection because the amplitude of negative sequence current is proportional to negative sequence voltage. When there is no negative sequence voltage, there is no negative sequence current injection.
Thank you. The second question is, if there would be a negative sequence voltage, then the negative sequence current needs to be generated, and this will most likely have some delay. So I think 30 milliseconds are specified for that. So question 2 is, are the controls fast enough to guarantee dependable and secure negative sequence elements operation in traditional tripping times, 1 to 1.5 power cycles?
Yeah, so this is so compare the performance of 50Q element under the type 4 German grid code to that under conventional synchronous generator. So you can see that here the operation of 50Q is a bit slower. There is a time delay here compared to the case of synchronous generator, and the cause of this delay is basically the rise time of GSC current control. So in response to your question, so yes, basically you can, the typical rise time of GSC for transmission level wind turbine generator is 10 to 20 milliseconds. But you can, of course, if this is not sufficient, you can reduce the GSC time delay, the GSC rise time basically in our case study, I think it was 5 milliseconds, the GSC rise time, and it delivered the desired operation time. But yeah, because it depends on control, by adjusting the control gains and time delays, you can achieve the operation time that is desired.
Thank you very much. Again, thank you for your presentation and for answering the questions.
Thank you.
So, you're welcome.